Hey everybody, welcome back to Physics with Dr. T. I'm Dr. T and we're going to go through this week a walkthrough on Ohm's Law. Now so far you've talked about electric fields and what that means for electric charges and making them move in space. Now we're going to turn our attention to more practical approaches to that, which is to have electric charges traveling through a conduit of some sort that they can travel through easily. Usually this is going to be a form of some kind of a metal, a wire. And so we're going to be looking at Ohm's Law and how electricity flows through wires and certain electronic components that we can use to control the flow of the electrons through those wires, namely resistors. But before we get into the science of all that, let's talk about this week's pre-lab activity. It's common in physics for us to take advantage of a strong analogy between the flow of water through pipes and the flow of electrons through wires. And so in this week's pre-lab, we're going to take advantage of that analogy and try and get a bit of an intuitive sense about the flow of electrons through wires and through resistors and other components that we'll talk about. And to do so, we're going to use something you don't expect to use. Now, we're not going to eat the electrons and we're not going to run current through these and test it that way. Instead, what you're going to do is use each of these in turn to run water over top of them. First, you use a simple butter knife, and you want to turn it so that it's vertical, so it's like this, and let the water run this way down the over the surface. And that's going to be a lot like what it's like for electrons traveling between, you can even imagine several knives, but the water traveling between those is going to move in a way that's like electrons traveling between layers of metal. And then you're going to take a look at water passing through the tines of a fork. And that water going through there is going to slow down, but it's going to continue on pretty easily in the same path that it was going. And that's a lot like how a resistor works. And finally, you're going to use a spoon to inhibit the flow of water and really kind of disrupt the flow of that water coming out there. Now, it's still falling in gravity, so this is going to be a limited experience on that one. But pull the spoon so that the water hits it and just creates a tube. It just sprays out. Now, if you turn the water down low enough, you'll accumulate some water into the spoon, and that's a lot like a component we're going to be studying soon called a capacitor, which collects all the charges that are coming up to it in an electric circuit. So between these three, you'll take a look at how the water is flowing, and hopefully you'll get a better sense of how electrons are flowing through an electric circuit. All right, so let's get back to the walkthrough. All right, so one of the first things that we talk about in theory is the flow of electrons through materials, and way of comparing and understanding the flow of electrons is thinking about the flow of water. We have a flow of water analogy. So if we think about water flowing through different type pipes, we think about, well, how fast does it flow? How much water goes through it? If you want a really tiny amount of water to go through, you use a really small pipe. If you want a lot of water to flow through, you use a larger pipe. This is a lot of intuitive material. So when we think about a smaller pipe, what makes it different from a larger pipe? Well, it's got a different cross-sectional area, which means it's got a smaller radius. And so when we have water flowing through a narrow tube, it takes more effort to get that water through. Whereas when we have a larger tube, it's a lot easier to move that same amount of water through because it'll fill the space so easy and there's not a lot of resistance from the flow of that water. Aha, resistance. So we think about the characteristic of metals, and one is the resistivity. So different materials will resist electricity to different amounts, but metals tend to conduct electricity very well. So there is a quality of materials that can resist the flow of electricity, and it changes from material to material. We refer to the resistivity as the quality of a substance to resist the flow of electric current. Similar to our water analogy, we have charged particles traveling through a wire, and that wire has a radius, which means it's got a cross-sectional area, pi r squared, and we have a length over which we're curious to know what the resistance is. So you measure the length of there, you measure this radius and calculate the cross-sectional area. So we would expect that for this type of configuration, that the larger the cross-sectional area of the wire, the easier it will be for electricity to flow. In other words, the larger the wire, the lower the resistance. So we write a formula that puts resistance and area in an inverse relationship. We expect that the natural characteristic of the metal to resist flow of electricity to be corresponding to the resistance of that wire. So we'll put those in a direct relationship. And the longer the wire it takes, the more power we have to put into trying to push those electrons through that wire. That's a little bit lesser of an obvious characteristic, but that's one that's not, it's an important characteristic nonetheless. So the longer the wire, the larger the resistance, so we again have that in a direct relationship. And so you'll be testing this relationship using the equipment that we'll be talking about momentarily. Okay, so now that we've explored a little bit of the idea of electric current flowing through wires and that there is a response by the wire to resist that flow, now let's take a look at some components that we would put into a circuit and have a specific response to the flow of that electricity. And what we'll use is Ohm's Law, which you can see written here. Now, this is not the format that you're used to seeing it. Even if it's just been introduced, you're used to seeing it in lecture as V equals IR. Voltage is equal to the current times the resistance. But in our lab activity today, we're not going to be looking at it in this way. We want to look at it a little more in this way, which is just a swapping around of the variables. But mathematically, it's more useful because now we can measure voltages, we can measure currents, and see what resistance is the result if the object is ohmic. And so what you want to do is set up your circuit similar in this way, where you have two multimeters, two digital multimeters. In the lab manual, you'll see DMM, digital multimeter. And all that is just a fancy tool that has multiple options for measuring different characteristics about electric circuits. So you take your DMMs and you'll configure them so that one will be an ammeter, it'll measure the current flowing through the circuit, and one will be set as a voltmeter to measure the voltage across a given component. Now, you want to be very careful about how you set these up because for the ammeter and the voltmeter, they have a different plug-in on the bottom surface. So make sure you consult your manual and carefully connect all your circuit before you turn your circuit on so that you don't risk damaging the digital multimeter ammeter configuration. So you'll be setting the Pasco system up for 10 volts and then you'll ramp it down 8 volts, 6 volts, 4 volts, 2 volts, 0 volts, the less obvious one, and then -2, -4, -6, -8, -10 volts as well. And as a result, you're going to be basically testing over this range of 20 volts whether or not the resistors and the light bulb are in fact ohmic. In order to be sure about whether or not they're ohmic, you'll create a plot eventually of your voltage versus current. And if your data comes out to be straight lines, then it matches this linear relationship and it should be an ohmic device. If the device does not follow a straight line, then we refer to it as non-ohmic. And the question you want to think about as you're writing your lab report is, what happens to the energy when we apply the voltage, which remember, the voltage corresponds to some power, some energy being applied to the circuit. What's happening to that voltage power? Where is it going in the circuit? Is it going anywhere? Is it being lost? Are we losing electrons? These are questions you want to think about as you are exploring this lab activity. For this week's lab, again, you'll be using a digital multimeter. This time you'll be using it both as a voltmeter and as an ammeter. And so here's one of the voltmeters that you will be expecting to work with. And here's another potential one that you may find at your desk. You'll notice that they are different brands, but they have the same basic layout. They have options to measure voltages, resistances, current flow, and for some of these you see that they have a direct current and an alternating current option. We're going to focus on the direct current for now. Now, in previous lab activities, you may have found that having these probes would be the better option, but we're looking at closed circuits that are in a stable state. So we can actually remove these for this lab activity. In their place, we can use what are called BNC or banana connectors. It's largely to do with the nature of the tip here. And for voltmeters, we'll connect the black into the COM, and the you see the voltmeter has the resistor voltage and another tool that you put into on this side, and you can adjust it as necessary. However, if you're using this as a current flow measure, also called an ammeter, we'll want to take this out and put it into here. Now you'll notice that if you tried to use this in any other setting, it gives off an alarm, so make sure that you've got your system completely set up and you've checked your current flow before you turn any power on and have this in an ampere measurement. You always want to start out the largest possible amperage, that way in case there's a little bit too much current flow you don't blow one of the fuses that are inside there. And as you need more information, you can turn it down to milliamps and then microamps if it's on that scale. For the first part of your lab activity, you'll be given a length of wire which is not exactly 1 meter, so don't make the assumption that it is. As part of the reason you want to make that measurement, tape this down to make it as straight as you can, and you can unbend certain parts. And then you'll connect these alligator clips to your probes or to your BNC connectors, and then clamp them on to a given edge. Try and get as close to the edge as possible, but make sure that you've got a good connection and watch for stability. Once you've measured the resistance of this using the ohm setting, the ohm meter setting of your multimeter, you measure the length, you'll get the vernier calipers and measure the diameter, and that's all the information that you'll need to calculate the resistivity and compare that to the given resistivity for nichrome. So for the second part, you'll be using this circuit array of available components and a switch in order to make your measurements. You'll take note, by inspecting this for a moment, you'll notice that there are an array of resistors that go across. We're not going to look at the 10 ohm resistor, it's very low. The 33 ohm is also kind of low, but you notice that there's a couple of banded resistors. These bandings are color-coded to tell you what the actual rating should be. They should match what you have written on the board, but you want to compare that to the chart that's available to you. This is a little bit of a practice ahead of the next lab that will be studying resistors in greater detail. But you also notice that there's a light bulb that's on here and a couple of components called capacitors. We won't be looking at this for this week, but they will be coming up. So take a few moments to inspect this and get more familiar with this. We'll be using this board multiple times. One additional safety component as far as the equipment is concerned is you can set up, instead of connecting directly your components to the power source and then beginning your power distribution, what you can do is connect one through your switch here, and that way when you're ready to go ahead and close the circuit, you can go ahead and close the circuit and then begin your observations. It's a much more stable way to control the operation of your circuit. So this week's lab activity is going to be submitted as a short lab report. So you're going to have the data that you collect about the wire, its resistance, its length, its cross-sectional area, and its resistivity, and you're going to compare that to the resistivity that is given for a nichrome wire. Furthermore, you want to have the data that you've collected for at least 2 resistors and 1 light bulb so that you can compare objects that are ohmic and clearly ohmic and objects that are clearly not ohmic. You also want to make sure that you have a graph that contains those. Now you can put those 3 onto the same graph. They should be in a comparable range of information, especially since we're using the same voltage ranges for the minimum, like I said, minimum of 3 objects. In the short lab report, remember that you want to challenge yourself to have a good, clear explanation of the theory. You don't want to take more than 2/3 of a page probably to do that. Don't forget to have your procedure described in a reasonable detail. You want your data section to be a display of the data, but not just data tables. You want to talk a little bit about the context of that data. Your data analysis section, on the other hand, needs to actually break down what went well. Why are there any discrepancies, smooth lines that shouldn't be smooth, or not smooth lines that should be smooth? Is there a reason for that? Explain it from the experimental experience. And finally, you want to have a good discussion at the end that zooms out and takes a look at the whole lab overall. What went well, what should be done differently maybe in a future lab in order to get better results or to get more convincing results. Once again, short labs really should run somewhere between 3 and 5 pages. Make sure that you're working on new ways of organizing the information on the data. Make sure you consult the 3 lab reference tools that show different forms of the short lab so that you can produce the best quality lab report that you have available to you. Well, that does it for another week of our walkthrough video. I'd like to remind you that if you have any questions, you can talk to me, talk to your TA, talk to your classmates. You really want to explore these ideas as best you can. This is a very rich area, and resistivity and resistances are actually of broad use across a lot of different sectors. Don't forget that we also have the Physics Help Center over in ID Weeks, and until next time, we'll see you in the laboratory. Which is to have electric cars.